should have waited to record until I had a functioning toolbar so that I would be able to actually write. There we go. Success. All right. We got a population of a city that is growing according to this differential equation. We should note that this differential equation is the differential equation for an exponential growth or decay. On a separate note, if you're typing questions in the chat, make sure you tell me which test you want them off of, because we've got like 5 different tests in the Google Drive there to look at. So just so yeah, I need to know what you. All right. So we have an exponential growth equation here. K is a constant. T is measured in years. The population of the city doubles every 12 years. So we know that this, and we could solve this as dp over p equals k dt. But we should know what that solves to, right? We already figured out what this solves to. That it solves to p equals p naught e to the kt, right? That's just what this basic exponential growth differential equation solves to. Like final amount equals initial amount e to the kt. So we know that the population doubles every 12 years. So that can help us to figure out what k is, because we know that the final amount, 12 times the initial amount, sorry, doubles, and not doubles, not 12 times, doubles, so 2 times the initial amount. Wow, I have written everything horribly here. Let's try this again. The final amount is double the initial amount. So 2 p naught equals p naught e to the k times 12, because it takes 12 years to do that. And we would hopefully note that we could cancel out the p naughts. And we take the natural log of both sides, we get natural log of 2 equals 12k. And so k is equal to, well, natural log of 2 over 12. And whatever that comes out to be.
Thank you.
Yeah, something like probably A or B is my guess.
It's A.
It's A. Look at that. Everybody okay there with number 90? All right. Number 12 from the 2013 test will be next. All right. This is a good one that we'll momentarily be showing. We want to know, for which of these functions does the limit as x approaches infinity equal 0? They're all fractions. So if the limit as we approach infinity equals 0, it means that the denominator has to grow faster than the numerator, right? That's what gives us 0 as we go towards infinity. If the denominator gets large much more quickly than the numerator does. So if we look at, for example, ln of x over x to the 99, ln of x goes towards infinity and x to the 99 goes towards infinity, but x to the 99 grows more quickly. So that's a yes on number 1. Number 2, they both go towards infinity, but e to the x grows more quickly than ln x. So that's a no on number 2. And number 3, they both go towards infinity, but e to the x grows more quickly than x to the 99. So that's a yes on 3. So it should be 1 and 3. Good or no? Any questions there on that one? All right. Next question is, nobody's asked another question. So I don't know. You should all have done lots of problems and probably have some questions. I literally spent the entire period during period 2 answering questions, and we didn't finish all of their questions from 2013, 14, and 15. So either you guys are brilliant by comparison or lazy by comparison, or some combination of the two. More questions? Does anybody have more questions? 22 from the 2013 one also, I assume. Okay. (22). Questions like 22 often trip people up, mostly because there's a lot to read and then you have to interpret and people don't want to read. So he says the function f is continuous for all real numbers. The average rate of change of f on the closed interval from 6 to 9 is -3/2. Okay, cool. For the values of c between 6 to 9, there is not one where the derivative is equal to -3/2. Which of these things must be true? So there seems to be an issue here, if we think about it. It says the average rate of change is -3/2, which means the instantaneous rate of change should be -3/2. This should be true if f is continuous and differentiable. Well, it says f is continuous. Does it say that f is differentiable? It doesn't say that f is differentiable. So what this is telling us is that f is not differentiable. We know it's continuous, but it's therefore it must not be differentiable because this is not true. Does that make sense to everybody for number 22? All the rest of those things are just things to confuse you. This is just the mean value theorem. It doesn't meet the initial criteria for the mean value theorem.
So if it's differentiable, then it's automatically continuous, but not the other way around?
That is correct. Right, because here is a function that is continuous. Yeah, absolute value of x is continuous for all real numbers of x, but it is not differentiable at x equals 0, right? But if something is differentiable, it must be continuous.
General question, when do integrals not exist?
When do integrals not exist? In what sense of the word don't exist do you mean?
In the sense of option B, like whatever they mean by that.
Oh, okay. Oh, right. Choice B there. That integral, you will not. The only way you in Calc 1 will come across an integral that might not exist is if you had some function where, like, you know, we went along to like A, and then there was just a complete gap here at B, and I said, like, oh, what's the integral from C to B of this function? Well, that wouldn't exist because there's just this big gap where there's no function in there. That is the only instance in which you guys might have an integral that doesn't exist. There are other integrals that don't exist, like values of integrals that don't exist, but they come up in Calc 2 in something called improper integrals, which I can just briefly explain because it's interesting. Suppose I have a vertical asymptote here and I'm looking at, like, you know, -1 to 7 or something. If I want the integral from -1 to 7 of my function, there's a possibility that this integral might not exist. Right? There's a possibility that one of these areas here is infinite, in which case the integral wouldn't exist. There's also a possibility that both of these have a finite amount of area and this integral does exist. So it's possible for this to exist, and it's also possible for it to not exist, but not something you need to know. The only possible case where an integral might not exist would be something weird like this happening. Does that answer your question?
Yes, thank you.
Sure. Is that more information than you wanted? Probably. Oh, well. Okay, let's see here. I got questions. I assume this is the 2012 test, not the 2021 test, because I don't know about the 2021 test yet. So question 9 from 2012, which I should probably open the 2012 test. Question 9. All right, we want this function f of x to be continuous at x equals 2. For a function to be continuous at a point, we have to have three criteria met. Three criteria for the definition of continuity. 1, f of 2 must exist. 1, the limit as x approaches 2 of f of x must exist. And 3, f of 2 must equal the limit as x approaches 2 of f of x. So in order for f to be continuous at 2, f of 2 must exist. Does it exist? Yeah, it's k. Check, done. Does the limit as x approaches 2 of f of x exist? Well, the limit as x approaches 2 of f of x is 0 over 0, right? Plug in 2 to this, you get 5 times 0 over 0, 0 over 0. So we can use either L'Hopital's rule, which seems unnecessary because we can just cancel out those x minus 2's. So we'll just say it's the limit as x approaches 2 of 2x plus 1, which is 5. So the limit as x approaches 2 is 5. So it exists, and it is equal to 5. And f of 2 is just equal to k. So k just needs to be 5. Good or no? This is a really common question. They like to ask things similar to that. Everybody good there? Any issues with that? Any problems? Any complaints? All right, next one is going to be number 11. Assuming I can get it to show up. There we go. All right, number 11. All right, number 11, f is the function defined by f of x equals the square root of the absolute value of x minus 2. Okay, which of these things must be true? So we may or may not be able to know what the graph of this looks like. It would be helpful to. The graph of this just looks like the square root of x minus 2, and then the opposite of the square root of x minus 2, just flipped over this other direction. This is an x equals 2. So if we know what the graph looks like, this should be pretty straightforward. We know that the function is continuous, but there's a cusp at 2, so it's not differentiable at 2. So that is our answer. But if we didn't know what the graph looked like, we would have to sort of kind of go through here and say we're not going to have a vertical asymptote, because a vertical asymptote only occurs when we get some number divided by 0, so it wouldn't be that. The limit as x approaches 2 of f of x is not 0. Well, I mean, if I plug in 2, I get 0, right? And I can plug in a number less than 2, and I can plug in a number greater than 2 because its absolute value makes everything positive. And so it seems like there's no reason why that limit shouldn't be 0, and it is. And there's nothing in here that is telling us that this is continuous here. I mean, that it's not continuous. I mean, we plug in any value less than 2, any value greater than 2, we can plug in 2. The limit as x approaches 2 is 0, like we just said, and f of 2 is 0, so it must be continuous there, just like from the last problem. And then to see that it's not differentiable, we've got to think about what's happening to this. If we plug in values of if we plug in values of x that are very close to 2 from the right, we're getting we're getting things like we're getting something that looks just like the square root of x minus 2. Right? But if we plug in values to the left of 2, so like 1.99999, we're getting something that looks like the square root of the opposite of x minus 2. And if I were to take the derivatives of each of these, 1 over 2 root x minus 2 and 1 over 2 root negative x minus 2 times negative 1, we would see that in one case up here on the top, this thing is positive, but this thing on the bottom here is negative, and therefore the slope as we approach 2 from the right is positive, and the slope as we approach 2 from the left is negative. And if those two slopes aren't the same, we can't have a derivative at the point x equals 2, so it's not differentiable. But easiest to know what the graph of that looks like. But you can go through and, by process of elimination, if you don't know what the graph looks like, figure out all the rest of it. Any questions there on number 11? All right, 19. All right, so we got a function that is x over x plus 2. We want the slope of the tangent line to be half. So basically, we just want f prime of x to equal a half. Well, in order to figure out what f prime of x equals a half, we need to find f prime of x. That's a quotient, x over x plus 2. So we use the quotient rule, x plus 2 times the derivative of x minus x times the derivative of x plus 2 all over x plus 2 squared. We want that to equal 1/2. So we should be able to simplify this. X plus 2 minus x is just 2. And if we cross multiply, we get x plus 2 squared equals 4, or x plus 2 equals positive or negative 2. And x equals, if we subtract 2, we should get 0, and we should get negative 4. So it looks like that should be choice C. And one thing that you'd want to be careful with is you want to go back in and make sure that both 0 and negative 4 are defined in your original function, which they both are. If they weren't defined in your original function, like for example, if negative 4 wasn't defined in your original function, then you have just chosen A. All right, next one is 24. We have g of x as x squared e to the kx, where k is a constant. We want to know for what value of k does g have a critical point when x is 2/3. Well, the critical point occurs when your derivative is 0 or undefined. So let's find our derivative. The derivative of x squared e to the kx,
that's going to be a product rule. So x squared, and the derivative of e to the kx is e to the kx times the derivative of kx, which is k, and then plus derivative of x squared times e to the kx. And we want g to have a critical point when x is 2/3. So we want probably the easiest way to do this here. Well, we just need to plug in 2/3 for x and solve for k. It's going to be a little bit of a pain to do that probably, but we should be able to factor out an x e to the kx. If I take an x e to the kx out of both of these, I'm left with kx plus 2, and then equals 0. And then if x is 2/3, we've got 2/3 e to the 2/3 k times 2/3 k plus 2 equals 0. Well, e to the 2/3 k is never going to equal 0. If I multiply something that's never 0 by 2/3, it's still never 0. So all I really care about is 2/3 k plus 2 equals 0, which gives me k equals -2, multiplied by 3 is -6, divided by 2 is -3. Good or no? Any questions there on 24? All right, next one is 26. So we have g, and the first derivative of g is this. It's an integral from a constant to x of a function, which must be true on 0 to 2. And everything we're talking about here is increasing, decreasing, and concave up, concave down, or points of inflection stuff. So first off, the derivative g prime should tell us if g is increasing or decreasing. So is g prime greater than 0, or is g prime less than 0 for x values between 0 and 2? Well, if I take e and raise it to any power, I always get a positive number, right? E to the -t squared is always greater than 0. So therefore, the integral from 0 to any x value, we'll say any x value greater than 0, positive x value, of e to the -t squared dt is positive because the function itself is above the x-axis. So we know that g prime is positive. So if g prime is positive, it tells us that g is increasing. So we can get rid of c, d, and e immediately because they're all decreasing. Then we need to figure out about concavity. So we need to find g double prime. Well, g double prime is the derivative of g prime. And the derivative of the integral from a constant to x of a function is just that function. And for all values from 0 to 2, and really for all values of g double prime, that's always positive, tells us concave up. And we can eliminate choice B because it says concave down. Good or no? All right, next one is 77. Then we're going to move back to the 2013 test. Let's see, 77. There we go. So we've got f as a function continuous on the closed interval 2 to 4. F of 2 is 10, f of 4 is 20. What is guaranteed by the intermediate value theorem? Well, here's the point 210. Here's the point 420. And we want to know which of these things must be true according to the intermediate value theorem. Well, the intermediate value theorem says that if I have a function that is continuous on a closed interval between 2 and 4, then for every value between f of 2 and f of 4, so for everything, we'll call them W, for all W, that looks absolutely atrocious. For all W on 10 to 20, there should be a C on 2 to 4 such that f of C equals W. And for every Y value between 10 and 20, I should be able to obtain that Y value by using an X value between 2 and 4. Well, this says f of x equals 13. That's a Y value between 10 and 20. And it says, oh, it must be guaranteed that I have one solution on the open interval 2 to 4. Yep, that's true. Done. Choice A. Choice B, f of 3 is 15. No, nothing said that this was linear. It could have been linear, but it didn't say that it was linear. It's not guaranteed by the intermediate value theorem. The intermediate value theorem has absolutely nothing to do with derivatives, so we can ignore that. And f attaining a maximum on an interval 2 to 4 would have to do with the extreme value theorem, not the intermediate value theorem, so we can ignore that too. Any questions there on 77? All right. Next question was from the 2013 test, number 80. All right, we got the position of a particle is S. S is increasing from 0 to 2 and decreasing for 2 to infinity. We want to know the total distance the particle travels from 0 to 5. Well, total distance should be an integral of speed. Speed is the absolute value of velocity. Velocity is the derivative of position. So if we want to know the total distance the particle travels from 0 to 5, it should be an integral from 0 to 5 of the absolute value of s prime of t dt.